This video is on electrolytic cells, which are similar to voltaic cells in that there's a conversion between electricity and chemical potential energy. There are certain things in common and certain things that are different. You may remember this device right here. This was called the Hoffman apparatus. And in it, what we did was we took water and we split it into hydrogen and oxygen. Oxygen came out one end and the hydrogen came out the other end. We collected it and I showed you the properties of those two. You might also note that it was connected to a power source. And the reason why is because this reaction is not spontaneous. Water doesn't just spontaneously break down into hydrogen and oxygen because water is more stable than hydrogen or oxygen. Matter of fact, they have cars that run on a mixture of hydrogen and oxygen. When you put them together, they react explosively. So these guys are unstable. So we're producing something that is essentially an endothermic process, okay? So first of all, it's not spontaneous. Second of all, it requires a power source. And the power source is going to be something that's DC, direct current electric. That means it could be a battery or a device that converts the AC from the wall into DC current. Now, what is the same about this? Before we get to IDing the anode and the cathode and other things here, let's talk about the anode and the cathode. There's good things here. It's not that confusing. The cathode is still going to be where reduction takes place. It's still going to be a place that the cations migrate. And when they get there, they're going to get reduced. The anode is still going to be the place of oxidation. And it's still going to be the place where the anions migrate. In some cases, the red cat will still get fat, and the anode will still get smaller in mass. All right? That didn't happen with the Hoffman apparatus because the two things that were produced were hydrogen bubbles and oxygen bubbles. So sometimes the electrodes are surfaces on which the reactants proceed. If the electrodes participate in the reaction, meaning they are a reactant or product in the reaction, then the masses will change. My electrodes in this device here were platinum, and platinum is an inert metal, and it's just a surface on which the reaction proceeded. What happened was the amount of water changed over time. It went down. All right. Now, there's also one other thing that is the same. There's always an electrolyte present. In this case, what you didn't see me do was that morning I put sulfuric acid in here. We hadn't talked about acids yet. Sulfuric acid obviously now produces hydronium ions. Therefore, it is an electrolyte and it conducts electricity. Okay, what else is different about this thing besides the fact that it's non-spontaneous and requires a power source? Well, the one thing I can talk about now is it contains only one chamber. And because of that, there's going to be no salt bridge. Right? This might look like a bunch of chambers, but they're all connected. There's sulfuric acid and water filling the entire thing. There's no one chamber here and one chamber there, one beaker here and one beaker there. So we're done with this, this, and this. We're going to come back to 3 and 4 as we look at the next diagram. This is showing the electrolysis of molten NaCl. Let's break that word down though. Electro refers to electricity. Lysis means to split. So we're going to split sodium chloride. Now, in a way, it's already split, right? It's molten. Now, remember, for it to be molten, the temperature's got to be really, really hot. The word molten implies hot. So we're talking like, maybe 1,000 degrees Celsius or something along those lines. Pretty darn hot, okay? Those ions are not floating around in water, all right? Now, we also have a power source. Now, the power source is written this way. You will never see this on the regents or any of the questions, so you don't need to know this, but since it's in the diagram they got from the internet, I should say something. The little small dark bar is a negative side of the battery. That would be the terminal of the battery that's negative, and this would be the terminal of the battery that's positive. If you look at batteries, they always say positive and negative. You can actually see them there, all right? Now, the other thing I should mention is the electrodes are made of graphite. Why? Graphite conducts electricity, but it doesn't melt at 1,000 degrees Celsius. Okay, you couldn't make electrodes of copper because they would melt if you put them in molten sodium chloride, and you wouldn't be able to do this. Okay, so what is going on here? Well, we have an external power source, and what that's doing is making one of the electrodes negative, and it's making one of them positive. Electrons are going in this direction towards the electrode that's negative because the battery, the power source, is pushing electrons there. This is not spontaneous. This is an external power source, right? Well, what's going to happen there? Well, because this electrode here is negatively charged, the positive ions, which are cations, are going to go there because opposites attract. So the sodium ions are going to go there, and when they get to the cathode, they're going to do what things do with the cathode. They're going to get reduced. So they're going to go from +1 down. What are they going to go down to? They're just going to go down to 0. They're going to get back their electron. They're going to go back to being 2-8-1, which is unstable. I'm going to put my 1 electron in over here. Now, the chlorides are going to go to the anode because they're negatively charged, and they're going to be attracted to the positive charge of the anode. So they're going to go there, and they're going to do what happens always at the anode. They're going to get oxidized, which means their number is going to go up. What's it going to go up from? It's going to go up from -1 up to 0. The problem with this is chlorine as an element is always Cl2, which means you have to balance this one for mass first by putting a 2 in front of it, and then you can put the 2 electrons over here. Now, what I want you to recognize is both of these products are unstable. So essentially what you did here is you took electrical energy and you converted it into chemical potential energy, because things that are unstable substances have a lot of chemical potential energy. Dynamite had a lot of chemical potential energy. We blew up sodium in class. The reason why these elements are never free in nature is because by definition they are unstable elements. They have a lot of potential energy as elements. Okay, so let's go back to the previous page. So you can ID the anode and cathode by it's determined by charge. Okay, the cathode will always be the thing that is negative because it will attract the positive cations, and the anode will always be the thing that's positive. It will attract the anions, which will then get oxidized there. The other thing you want to recognize is the energy conversion, which is the opposite. The voltaic cells are batteries. They take chemicals and make electricity. The electrolytic takes electricity and you produce chemicals that are unstable. So you convert electricity into chemical potential energy. So those are the differences. It's not spontaneous. You require power, electricity, and that electricity, that energy is then stored in chemicals which have high energy. There's only one chamber, and the anode and cathode are not determined by table J, but by the charges on the electrodes. I'm not going to write the summary equation here because I want to get to the last thing. Electroplating. Electroplating is an example of an application of the electrolytic cell. You have lots of examples of these. If you own a ring that you bought for $5 because it looks like gold, but it's not gold, it's because what they did was they put a cheap metal and they placed a thin coat of one metal over another metal. They can use this to make things pretty, like they can put a thin layer of, let's say, you can put a thin layer of gold over a ring, okay? They can use it for protection. Often iron or steel is covered with a thin layer of zinc. Nails are said to be galvanized. So if you know somebody who's a roofer, or you've ever seen somebody putting roof house, they use galvanized nails. You can buy these at hardware stores, okay? And they protect the iron underneath. The galvanized nails with a thin layer of zinc will last for several years longer than iron nails, and it costs a lot of money to replace a roof. Even more to replace a bridge as it slowly rusts out. So if you produce galvanized steel, which has a thin layer of zinc, the steel lasts longer. They even use it for silver plate. If you buy a silverware set nowadays, unless you go to a very pricey place, most silverware sets are not pure solid silver because they cost several $1,000s. My grandfather was a silverware salesman. Okay, he sold it to people who could afford to buy sets of silverware. They don't have silverware salesmen anymore because not many people buy it. What they do buy is they buy silverware sets with a thin coating, okay, of silver like this. Okay, so it looks like silverware, but it really isn't. It only has a thin coat, and the coat is so thin it costs pennies per utensil, realistically. Now, how do they put this thin coat? Oh, by the way, my favorite example of this is chromium. Like if you like old cars with the pretty chrome bumpers, those are not solid chrome. Okay, or the Chrysler building. So they put a thin layer of chrome over steel and it looks shiny and cool. Continuing. Note the same thing. You have a source of energy up here. You know that this is negative, so this is going to be the cathode, and this is positive, so that's going to be the anode. This is a bar of pure silver. This is a key on which you want to coat silver. Okay, you have an electrolyte, again, silver nitrate. The nitrate here is going to be the spectator. Now, this is going to have no net reaction because essentially what you're going to do is you're going to oxidize the same metal that you reduce. So what's going to happen here at the anode is the nitrates are not going to migrate there and get oxidized. The actual anode is going to get oxidized. So what's going to happen here is the Ag is going to turn into Ag plus. And the reason why it's doing it is this power source is pulling electrons from here, and they're going to here. Okay, and so the silver atoms are losing their electrons and forming into silver ions, and this is going like this. So what's happening is the anode is now going to keep getting smaller because what's going to happen is the solid silver is turning into silver ions. What's going to happen on the key, however, is this: the silver ions that are in, okay, that are probably in a molten state, it probably wouldn't be silver nitrate, but it's very complicated the way the action is, are going to go to the cathode where they're going to gain one electron and turn into silver atoms. Now notice what's happening here, okay? Essentially, there's no net reaction. What's really happening is silver atoms are moving from here and they're going onto the surface of the key. But you still have the red cat getting fat because the silver ions are being reduced at the surface and they're going from ions to silver atoms. And so you're putting a little plate, a little thin layer of silver on the surface. This is done all the time. In summary, electrolysis is just like it's very similar to a voltaic cell. You're still having oxidation happening at the anode. You're still having reduction take place at the cathode. The key thing is you can't use table J now. You're going to look at these charges. Whichever side, the positive electrode will always be the anode. The negative one will always be the cathode. Okay? There'll be only one chamber. You notice in both these diagrams here and here, there's just one chamber. There's not two chambers. There's no salt bridge. All right? You're going to require a power source. In both these diagrams, you see a power source, and in my original diagram, there's a power source. All right? And the big thing is you're taking electricity and you're converting it to chemical potential energy. That's not really true of the electroplating situation, honestly, but in a situation in which you're actually taking a compound, splitting it like in this situation right here, or on the first page, when you do these decomposition reactions, you tend to end up with elements that tend to be unstable. So in most of these cases, you are basically doing something that you're taking electricity and you're creating something that is unstable and has a lot of chemical potential energy. Remember though, what happens at the anode, what happens in the cathode is still the same, and there's still an electrolyte present. I hope this helps.